Hi guys, so we're ready to start section 5.2, which is finding theoretical probabilities. So some key things we're going to look at are find theoretical probabilities of equally likely events, be able to find the probability of a complement of an event, and then also use some basic probability rules. So this first slide is looking at probabilities, right? So these are some facts about probabilities. So a probability is always going to be in between 0 and 1, and a probability could be equal to 1 or 0, right? Either it can be equal to that, right? So how we can write that in symbols is the following. So we have the probability of x in the middle. So we're saying the probability of x has to be bigger than or equal to 0, but also less than or equal to 1, right? So it's in between 0 and 1, and that's inclusive. We say that's inclusive, right? Meaning it can be 0, it can be 1. So we can express probabilities as fractions, decimals, or percents, right? So in certain situations, it might be more helpful or more convenient to show one or the other, but we can do either one, right? Either one of those. So then, just to point out, if something has a probability of 0, that means it will never happen, right? That's 0% probability. Where if something has a probability of 1, then that's equal to 100%. So that means it's guaranteed to happen, right? Certain to happen. So one thing you want to kind of note is that when something's 100%, it means it's going to happen no matter what. Like there's not one possibility that it can't happen, right? So that's a really strong word to say something will always happen or something will never happen, right? So for example, you might check on the weather and something might have a 100% chance of rain. That kind of number kind of bothers me because maybe it won't rain. Maybe it's not raining at that moment or in a specific spot, right? So personally, I don't like when like a news like weather.com or Weather Channel will say 0% or 100% probability. I would never say those for certain, right? Because we can't predict the future that to that degree, right? So you want to make sure you make note of that. So then another thing that I want to show, and I talked about above, is this probability notation. So usually we find a probability of an event and we let capital letters represent the event. So like here, I give you A, B, and C, and so forth, and up above we used X, right? So typically you're going to find like here's an example I have here. I'm saying toss a coin. Let A represent the event that the coin lands on heads, right? So you can write the probability of A is 1/2 or 0.5 or 50%, right? So let me draw this in for notation, right? So oftentimes you might say like let A equal the event of flipping a head, right? So we could write it like that and then say, well, the probability of A would be 1 out of 2, right? There's only one head on a coin out of 2 possibilities. You could get heads or tails, so this is 50%, right? So you could use that notation. And if you were going to reference A a lot, that this notation might be convenient because you could just say at the beginning, like, hey, this is what A is, and then you can just reference A below and not have to write down all of that, right? Or you could do like probability of getting ahead, right? Or maybe shorthand it, just use H, right? So those are all common ways to denote that, right? So then the next slide is looking at, well, what does it mean to be a complement of something? So complement of something is just the opposite, if you will, right? So if you remember like a Venn diagram, right? So like here is our Venn diagram. We call this the universe, right? So everything I want to talk about is going to be in this box, right? And then I can have a set A in here, right? So anything inside of here would be A, right? And then if we want to talk about A complement, that would just be everything out here, right? Everything that's not in A, right? Everything that's outside of A, right? So you can think of it like that, right? That's from a very theoretical standpoint. Or let's say our set B, let's say set B is equal to Ohio, right? And let's say we're confined to the USA, right? So if the box is USA, and then here my set is Ohio, then the complement, right? B complement would be everything that's not in Ohio, right? So it'd be everything outside, right? So that'd be like Michigan, Florida, Texas, right? Everything that's out here, everything that's not in Ohio. So all the other states, right, would be the complement. So all states minus Ohio, right? So hopefully that'll help, right? So here we're just reading this as the complement refers to the event not occurring, right? So complement of event A is written as A with a C as like an exponent, right? That's how we denote that. So here's another example, right? That might help. So if we're tossing a coin, right? If A is that the coin lands on heads, then A complement is the coin does not land on heads, right? So in other words, there's only two options when you toss a coin, right? Heads or tails. So this would just be tails, right? In this case, because there's only two options. And one thing to note is that the probability of A plus the probability of A complement is going to equal 1, right? Because either A happens or it doesn't happen. It can't be in between, right? So that's something to note. Probability of A plus probability of the complement is equal to 1, right? So here's another example. Wait for a bus and know its arrival time. So A is the bus arrives on time, and A complement is the bus does not arrive on time, right? So it's either one or the other. Right? So here I mentioned this. So the probability of an event and its complement. So the probability that A does not occur is equal to 1 minus the probability that A does occur, right? So if we write that in symbols, that we can just shorthand this here. So the probability of A complement is equal to 1 minus the probability of A, right? Or in other words, again, just to denote that, the probability of A plus the probability of A complement is equal to 1, right? Which is saying the same thing, right? So that's how you can remember that, is that they both add up to 100%, right? Either A happens or it doesn't. It can't be anything in between, right? So here's an example. It says, let A represent the event the candidate wins an election. So suppose the probability of A, that candidate winning an election, is 70%, 0.7. Then A complement would be, well, what's the probability that the candidate doesn't win, right? So we would take 1 minus the probability of A, and we get 0.3, right? So there's a 30% chance that the candidate will not win, right? This is the probability of A complement, where 70% is the probability that the candidate will win, right? Alright, so some more definitions here. We have to talk about sample space. So sample space is the set of all possible equally likely outcomes of an experiment, right? And we'll talk about some examples with this that might help you be more familiar with these terms. And then event is any collection of outcomes in the subspace, right? So so let's look at a couple examples, right? So on the next slide, here we have some experiment we're doing. We're rolling a fair die one time, right? So my sample space is the following, right? So the sample space, we can denote that as capital S, right? Is the set 1, 2, 3, 4, 5, and 6, right? So if I roll a die, a 6-sided die, these are my only options, right? 1, 2, 3, 4, 5, or 6. So we could look at different events, right? So like here, one event is, well, what if I want to roll an even number, right? So these are the set of outcomes that match the event, right? So notice we're just picking out what numbers in the sample space match that, right? So if I want to find the probability of getting an even, right? There's 2, 4, and 6, right? So there are 3 numbers out of 6 numbers, so that's a 50% probability, right? Whoops, jumped down. All right, so this would be 50% probability. So if we want to look at what's the probability of a number less than 3, right? So let's say rolling a probability where my number is less than 3, right? So we could denote it like this if you wanted, right? So now I'll do this in red. So my options are, well, I can get 1 or 2, right? 3 is equal to 3, so it's not less than 3, right? It says very specifically less than 3, so that means it can't be equal to 3. So there's only 2 numbers out of 6. So this would be one third, so 33% roughly, right? If we round to the nearest percent, it'd be 0.333 repeating, right? So the next slide is kind of showing what I already did. So to find a probability of something, you're going to count, well, how many times can that happen in A, right? So for example, above, we want to find the probability of getting, well, here we're looking at an example I just did. So if we roll a die, what's the probability of getting a number less than 3, right? So what's the probability that I roll a number less than 3, right? So we need to figure out, well, how many outcomes in A satisfy that, right? So if this is my sample space, right, then the numbers 1 and 2 fit that, right? So then that number goes in the numerator, right? There are 2 options. And then now you look at, well, what are the number of all possible outcomes, right? Well, I have 1, 2, 3, 4, 5, 6 different outcomes, right? 6 things to choose from. So the probability is 2 out of 6, right? So we can reduce that down as 1/3, right? Or again, we can show decimal or a percent, right? Whichever you'd like. Right. So here's another example of finding a theoretical probability. So here, let's consider a family has 2 children. Let's find the probability that both children are girls, right? So to do this, it could be helpful to make a table, right? So maybe here we write the first child. So the first child could be a boy or it could be a girl, right? Those are the only 2 options. And then for the second child, that could be a boy or a girl, right? So then it's possible that we could have 2 boys, right? It's possible that we could have a girl boy. It's possible that we could have a boy then a girl, and then it's also possible we get 2 girls, right? So those are the outcomes, right? That's the sample space, right? That's the total number of outcomes. There's 4 outcomes there, right? 1, 2, 3, 4. Now event A, what we're talking about is what's the probability that all are girls, right? So if I want to find the probability of A, where A is the probability that they have all girls, right? There's only one scenario, one outcome that has that happening, right? So this would be 1 out of, there's 4 outcomes total, right? So 25%, right? Is shown here, right? So it's 25% chance that both will be girls. And there we're assuming that it's equally likely to have a boy or a girl, right? That might not be the case, but we're looking at the most easiest examples of probability at the moment, right? So now we want to explore looking at some things that are and or probabilities. So here we're looking at, well, let's say we want to combine events with and, right? So an event belonging to A and B must belong to both A and B, right? So if we go back to a Venn diagram, right? So where what's inside this circle is A, what's inside this circle is B, right? Then A and B would be here, right? Where they overlap. So this is A, and B, right? And in mathematics, we use this symbol for and we use this symbol for or, right? So if how I remember it is the one that you can draw a line and make an A, that's the one that's and, right? So notice how I can draw a line across and that makes an A, or here if I draw a line across that makes an upside down A, right? So this means and, right? So this symbol is and this symbol can be thought of as or, right? So we use these symbols when we talk about sets in mathematics, right? So you might see that in the text also, right? So here's the example. So it says if event A represents wearing a hat and event B represents raising a hand, then someone in A and B is wearing a hat and raising a hand, right? So if we go to the next slide, there is a picture, and we're trying to find, well, what's the probability? So what's the probability that someone's raising their hand, right? And what was the and? Oh, wearing a hat, right? So notice probably raising your hand and a hat is the same thing as probability of wearing a hat and raising your hand, right? Those would be the same. So we're looking for people who are wearing a hat and raising their hand, and there are, what, two of them, right? One here. So Maria and David, right? So notice that, what was that? I can't read that very well. Maybe Rena. She's wearing a hat, but she is not raising her hand, right? So they have to fit in both with and, right? And means they both have to be true. They both equal. So if we wanted to find this probability, right? There's two people out of what? 1, 2, 3, 4, 5, 6 people total, right? So this would be 1/3, right? So here I have 2 6, but this would also be 1/3, right? Reduced, or 33% roughly, right? There's a 33% chance that that is happening, right? Where if I go down to or, right? So here it says an event belonging to A or B must belong to A or belong to B, right? So you could be wearing a hat or you could be raising your hand, right? Or both is okay, right? So the probability of A or B, right? In this case, so we would count Rena. So you just go through, right? Mike is not wearing a hat or raising his hand, so he's not good, right? Rena is. Maria is raising her hand and wearing a hat, so she's good, right? Alan, he's not doing either one, right? Or John, and David is doing both, right? So they would fit in the or category, right? So then so there's what, 3 people total out of 6, right? So this would be 50% probability, right? And if you want to go back to a Venn diagram to make sense of it that way, then the box is, everything in the photo, right? That's our U. Where here I would have, so set A would, we could let that be maybe raising your hand, and set B, we'll let that count the hat, right? So let's identify who would be in what spot, right? So if we look at Mike, he's not raising his hand and he's not wearing a hat, right? So Mike would be listed out here, right? So he's in the box, but he doesn't fit in one of these circles. He doesn't fit in that group, right? Where Raina, she is wearing a hat, so she would go here, right? Maria is doing both, so Maria would be in here, right, in the middle, right? That's raising her hand and wearing a hat. So the next person to look at is Alan. So Alan is like Mike, right? He's boring. He's not doing either one, right? So Alan would go here. John is also not doing either one. And then we have David, who is also doing both, right? So he would go here, right? So that looking at it from a set from a Venn diagram point of view, right? Those are where the people would fit, right? All right. So I added this slide in. So you're going to want to add this in your notes, right? I didn't put this in the original PowerPoint set that I put on Canvas, but you could just write this down, right? So mutually exclusive events are two events that cannot both be true or both occur at the same time, right? So if we talk about something that's not mutually exclusive, that means that it could happen at the same time, right? So another way to think about finding probabilities is from two-way table. It's kind of thinking about it from a set point of view, right? Where each one of these boxes belongs to its own group, right? Where like this 242 number are the people who are happy and they agree, right? Where this number is people that disagree and are unhappy, right? So you can't be in more than one of these categories, right? You're put into one of these boxes depending on how you answer this survey, right? So this is a general social survey. So they're asked about your happiness and also if you agree with the statement. In a marriage, the husband should work and the wife should take care of the home, right? So the following table summarizes the data collected, right? So if someone said that they were happy and they don't know if they agree, right, then they would be put into this group here, right? They don't know and they're happy. So we would just see who answered this, right? And there are 65 people that answered that, right? So hopefully you're getting the two-way tables okay, because two-way tables can be very useful very useful way to organize our data, right? All right, so let's go to the next slide. So we're just keeping the same table, and we're asked to find these three probabilities, right? What's the probability of someone being happy and agreeing? What's the probability of someone being happy or agreeing? Or what's the probability of someone agreeing or don't know, right? So let's look at these. So if we want to look at what's the probability that someone is happy and they agree, that would be this number, right? That's how many people fit in that category. So we'd take 242 and then divide it by the total. So here is where the total is listed, right? 1,146. So doing that, we get 0.211, right? So that's the probability of someone being happy and agree, right? So again, remember, I could show it like this: happy and agree, right? Or if I said something, like let A be equal the event of someone answering happy, right? And maybe let B equal the event that they answered agree, right? So you could spell it out, more like a sentence if you wanted. So then the probability of A and B would also be the same thing, right? 242 out of 1146, right? So then the next part that we were asked to look at is, well, what's the probability that someone is happy or they agree, right? So the total number of people who are happy or agree is the following, right? So all the numbers in red, right, would fit into this. Right, so those are all the numbers that we're considering, all the ones that satisfy what we're trying to find. So that goes in the numerator, right? So we add those all up, we get 1036, right? And then we still divide by the total number of people, right? And we get about 90%, right? That fit in those categories. So if we go down to part C, it says what's the probability that people agree or they don't know, right? So the total number of people who agree or don't know would be adding up these red values, right? So these are people that agree, these are people that don't know, right? So if we add all those up, we get 382 and divide by the total, we get roughly 33%, right? So when we count the number of people who agree or don't agree, nobody could be in the same category, right? So you're either here or you're over here. So we say those are mutually exclusive, right, as I said before. So it's not possible for both to happen at the same time or for someone to be in both groups, right? But if we wanted to find the number of people who are happy and they agree, then these would be not mutually exclusive, right? So what happens is we're going to be counting one group of people twice, right? So let's take a look at what I mean here, right? So this just shows that it's possible that we might count a group twice, right? So in general, when you want to find the probability of something of A or B, this is the equation we get, right? So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, right? So then it says, note, if A and B are mutually exclusive, then they cannot happen at the same time, so probability of A and B is 0, right? So let's look at a more concrete example to make sense of this, right? So let's consider rolling a die, right? So let A be the probability of rolling a 3, and maybe let B be the probability of rolling an odd number, right? Then my my sample space, right, S, is still 1, 2, 3, 4, 5, 6, right? And then, so if I want to find the probability of A or B, then I need to think about, well, how many ways can this happen, right? Well, my odd numbers are 1, 3, and 5, right? So there are 3 options. And then rolling a 3, I also have only one option, right? So if we're just using that definition, we would have 3 odd numbers plus one number 3. And then how many options are there total? There's 1, 2, there's 6, right? So one might think that this is the probability, right? But what the problem is with this line of thinking is we can't count 3 twice, right? 3 fits into both categories, but we should not count it twice here, right? There's only 3 numbers I can get to satisfy this, right? I can get 1, 3, or 5, and that will satisfy rolling an odd or rolling a 3. So what this is saying is we need to consider, well, what's in the set A and B, right? So in other words, what number is a 3 and also odd, right? Well, that would be the set of 3. So we have to subtract that out, right? So the probability of A or B can be thought of as the probability of A plus the probability of B, and then we need to subtract out the probability of A or B, right? Or excuse me, probability of A and B, right? What's common, right? So maybe drawing a Venn diagram will help here. So let me draw one. Oops. Let me make it a little bigger. So let's say that's A, and there's B, right? Oops, and this shouldn't be outside of my box, but it'll be fine. Right? So A, right, we let A be what? Rolling a 3, I believe, right? Rolling a 3, right? So this was, just to make notes, this was getting a 3, and this was getting an odd. So my only options are 1, 2, 3, 4, 5, and 6, right? So where would each of these numbers fall, right? So 1 is odd, right? So that would go here. 2 is neither, so 2 is going to be outside the circles, right? But inside the box. Like those don't fit in any of the categories. 3 is odd. And then we have what, 4 next. So 4 is not either of these, so that goes there, right? But I put 3 in the wrong spot, right? Did you notice that? So 3 is odd, but 3 is also a number 3. So this 3 needs to go in the center, right here. Right? So remember, inside of here, this is where A and B live, right? That's where A and B overlap. So we got 1, 2, 3, 4. Now I need to put 5 somewhere. So 5 is an odd number. And then we have 6, which 6 doesn't fit in any of these, so that goes outside the circle, right? So when we do this, we can't count 3 twice, right? Can't count twice. So this equation will help us fix that, right? So the probability of A happening is 1 out of 6, right? There's only one number that's a 3 out of 6 numbers. Probability of B happening is 1, 2, 3 values, right? We have 3 odds, so this would be 3 out of 6. But then I have to subtract if we have anything in common. Well, we do. We have one number in common. So this would be 1 out of 6, right? So if we do this, these cancel out. We ended up getting just 3 out of 6, which is the true probability, right? So again, these events are not mutually exclusive, right? So we have to use this, right? If they were mutually exclusive events, then this in the middle would be empty, and so we can just use this equation, right? So let's look at some more examples. So here we're rolling a fair-sided die. Find the probability of getting an odd number or a number greater than 3, right? So notice it's different than the example I just did. And then part B is, let's say you want to roll a number less than 3 or roll a 6, right? Let's look at these probabilities. So if you want to roll an odd number or a number greater than 3, right, then we have to look at the following, right? So A is, we'll let A be getting an odd, and let B be equal to a number greater than 3, right? So that'd be like rolling a 4, 5, or a 6, right? So we have to look at, remember the formula is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, right? So the probability of A happening, so how many odd numbers are there? Well, there are three odd numbers, right, out of 6. So it'd be the probability of getting an odd is 3 out of 6. The probability of B happening is also 3 out of 6, right? There are 3 values bigger than 3. We have 4, 5, and 6. And then we have to subtract if there's anything in common, right? So in other words, is there a number that's bigger than 3 and odd, and that's 5, right? So there's 1 out of 6 options, right? So we have to subtract this guy, right? So this ends up becoming 5 out of 6, right? Which is also here. So I just wrote it off to this side, right? And note here, these are not mutually exclusive because 5 can be in both, right? So 5 is a member of A and B. So those are not mutually exclusive. So the second probability we want to look at is, what's the probability of rolling a number less than 3 or rolling a 6, right? Well, these are mutually exclusive, right? We can't have a number that's less than 3 and also equal to 6, right? So in other words, if we draw a Venn diagram, right? So my options are, my sample space is 1, 2, 3, 4, 5, or 6, right? The box is my universe, right? What I'm considering, so we let that be U. So if I let this be A and this be B, right? So where I'm letting A be less than 3 and B be 6, right? So B would contain just the number 6, right? So let's just go through. 1 would be less than 3, right? So that would go here. 2 is less than 3, so that goes here. 3 is not less than 3. It's not equal to 6, so it would go on the outside somewhere, right? 4 would go outside of here, and also 5, right? So notice in the middle, right here, this is where the A and B are. There's nothing there, right? It's empty, right? So A and B is empty. And how we show that in mathematics is we use a null value, which is a 0 with a dash through it, right? So this is null. It's not the same thing as 0. It means it's empty, right? So a set of 0 is not the same thing as nothing in there, right? Those are not equal, right? So it's empty. So in other words, the probability of A and B happening is 0, right? 0 out of 6. It can't happen, right? So we don't have to use that equation, right? But I would recommend always using this equation. So this should be a minus, right? Minus. I would recommend using this equation still, though, right? Because if this number is 0, not a big deal, right? The probability of A happening, oh, there's 2 out of 6, right? The probability of B happening is 1 out of 6, right? And, oh, there's nothing that can be both, so it'd be 0 out of 6. So we end up getting 3/6, or a half, right? So I think this, using this equation every time is safe, because then you don't forget to subtract this off if you need to, right? All right, so that's the end of this section. So that should get you through the homework. If you have questions, make sure you email me. Thanks.